Lesson 33-3 is going to talk about spheres and solids of rotations. So we're going to learn some properties about spheres and their cross-sections, and also identify three-dimensional objects generated by rotating a two-dimensional object. So open your Springboard book. We are on page 489. Okay, so let's talk about a sphere. Okay, so a sphere is the set of all points in a space that are a given distance, which is our radius, from a point, which would be our center. Okay, so here's a picture of a sphere in your book in number 2. Okay, so they're talking about the sphere would be an unlimited amount of distances, our radii, that are spun around to create this 3D circular figure. Okay. So question 1A is going to have us to consider the cross section of a sphere. So I'm actually show you a GeoGebra, okay, which is going to show you the cross section, and that'll help us describe the shape and size of those. So let me pull up that. Okay, so here we have a sphere and that cross section, that plane that cuts through that sphere. So you can notice if I move this up or down, okay, what do you notice about the shape of the sphere? Okay, and the size as we move it up and down. Okay, well, hopefully you noticed that, okay, the cross sections are circles that just vary in size. Okay, they change sizes as you move it up and down. Now, even if I tilt this, okay, I tilt my cross section and move it, if you notice, it's still going to be a circle, okay, because the sphere doesn't matter kind of which side you're looking at. If it's round, it's going to be a circle no matter what. And even if we turn it, okay, tilt it so it's different ways, I'll turn it so you can see. You can still see it's going to be a circle no matter what. Okay. All right, what is the center of the largest possible cross-section of a sphere located in relation to the center of the sphere? So when I looked at my cross-sections, let me move this back, turn it so that tilted so it's backward. There it is. Okay, where on here, when we do our cross-sections, where's the biggest circle that we're going to have? Think about that. So if I move this up and down, it gets bigger, goes back smaller. So when do we have the biggest, the largest possible cross-section of our sphere? Where is that located? Okay. So in this part, it'd be the center of the great circle coincides with the center of the sphere. Now that leads us to this math term over here. The intersection of a plane through the center of the sphere is known as the great circle. So in this particular idea, our cross-section, the great circle would be basically when it has the diameter or the radius of your sphere. Okay, so when those kind of meet with each other. Okay. So when we talk about our sphere, when we talk about a chord of a sphere is the same thing as the chord of a circle, okay? So if it says to write a different definition for a chord of a sphere, okay, that is just a chord is a segment, okay, whose endpoints lie on the sphere. Whose endpoints So it's the same thing as from when we did it with a chord of a circle. Now we just have a sphere. So a chord could be like if it goes from here to there. Okay, that would be an idea of a chord. So the definition for the diameter of a sphere is, okay, same idea. Maybe I'll type this one in to save myself some space. Okay, the diameter of a sphere is a chord that contains the center. Remember, diameters are chords, but chords aren't always diameters. So in this problem, or in this picture, our chord goes from endpoint to endpoint. It would just have to pass through the center to be considered a diameter. Okay, last thing, do you guys remember what a tangent line is? Okay, a tangent line, or in this case, a tangent plane. How would you describe the definition of a tangent line or plane to a sphere? Okay, well, remember, a tangent line is a segment that intersects the sphere at exactly one point only. Okay, so if we draw this in, maybe I'll do this one in blue. Okay, if we have a point on the sphere, the tangent line intersects only at that one point. So it kind of runs alongside the sphere. That would be our tangent. Okay. And one last question on this part. If it says, what must be true about a plane that is tangent to a sphere and the radius? So do you guys remember when we did this before? What do we know is true about the tangent line and the radius that connects to that tangent point? Okay. Hopefully you remember that those were perpendicular to each other. The tangent line is always perpendicular to a radius. So I know my picture doesn't really look perpendicular, but that should always be true. So anytime, so again, the properties of a circle are very similar to the properties of a sphere. We're just applying them now in a different way. Okay. We're going to move on next to this new vocabulary word, so which is the solid of rotation. Okay, so a sphere is created by rotating a semicircle about a line. Okay, so if I were to take the semicircle and spin it, it should create that 3D circle. Okay, our sphere. So rotating a plane about a given axis, okay, such as this, forms a three-dimensional figure. When it does that, we call that our solid of rotation. So the picture that we get out after we rotate it would give us a solid of rotation, so a three-dimensional figure. Okay, so let's look at this picture here. We have this rectangle. Okay, if we were to rotate this rectangle around this line M here, if we were to spin this rectangle around it, what solid would we generate then? If we have this rectangle and we rotate it, we spin it in a circle, what kind of solid would we generate by rotating this plane? Okay, well, that would give us a cylinder, right? So think of this as like the label on a soup can, for example. If you were to roll that around and make it a circle, so basically connect your two ends, so put AC and connect it to BD, you should form a circle, okay, a cylinder shape. All right, let's jump to the last question we're really going to cover today, which is number 4. Here we have this triangle on this plane here, this XY coordinate plane. Sketch and name the solid generated by rotating the triangle about the x-axis. So if you took this triangle and spun it, okay, about the x-axis, what solid would we form then? Okay, that would give us a cone. Okay, so it's a little hard to visualize this one as much, but again, if we took this and we just kind of rotated it so we connected it from corner to corner, okay, we would create a cone. So notice when we're doing these solids of rotation, we always are going to incorporate a circle somehow. So think about the circle base and look at the shape you're given. What kind of lateral face would that make on our 3D figure? So this was a triangle, forms the cone shape. When we had a rectangle, forms that cylinder shape. Okay, so we will practice this more in class. But again, the key idea of today is just knowing those properties of a sphere and realizing that their cross sections would still be circles. Okay, they just vary in different sizes.